In this video I show you how to increase statistical power. I show you 15 strategies for higher statistical power in your analyses. The first is the obvious one: you could increase the sample size. But I think you already knew that. The second one, if you have a directional hypothesis, you could use a one-tail test instead of the more common two-tail test. For instance, in a correlation or a regression, if your hypothesis implies a positive relationship between the two variables, you could test into one direction, and that gives you a higher statistical power. Or if you're comparing two groups and you know or think you know which group will have the higher value, you could do a one-tailed t-test. Here I show you an example with a t-test for independent samples using G-Power, the power calculation software. For a two-tailed test with certain other parameters, I need 128. For the same parameters with a one-tailed test, I only need a sample size of 102 to get to the same power. The next very important strategy is increasing the reliability of your measurement instruments. Again, I'll show you an example, in this case a correlation analysis. Let's say that the correlation is 0.3 between the constructs. That is, if we had perfect reliability, that is a Cronbach's alpha of 1 for both variables. And with a power of 0.8, we would need a total sample size of 82. If, however, the reliability is very good but not perfect, let's say a Cronbach's alpha of 0.90, then we would have an effect size of 0.27 instead of 0.30, and the sample size would increase to 102. And if we had a rather low reliability of 0.7 for both constructs, then the effect size would decrease to 0.21 and the sample size would increase to 173. So reliability is a big deal, especially in correlations and regressions. So it makes sense to invest some time to find a very good measure, not taking the first measure you can find in the literature for the construct you want to use, but really try to get high quality measurement instruments, because you need much lower sample sizes to get to the same power with a high quality measurement instrument. Then you should have no floor effects and no ceiling effects. So you should make sure that your measurement instrument is tailored to your sample. If, for instance, you use a measurement instrument that was made for clinical population and use it for non-clinical samples, you could get into floor effects or ceiling effects, so that it's not able to differentiate enough for your sample. Next important topic, homogeneity of the sample. Most statistical tests work by contrasting some effect to some error variant, in most cases to the standard error. And the standard error goes down if you have a more homogeneous sample, because there you have less error variance. That's one of the reasons why many studies employ very strict exclusion criteria. There's a flip side to that coin. If you're using exclusion criteria, you could get to a sample with a high statistical power, where you will get a significant result maybe, but you're damaging your external validity. For instance, for psychotherapy, if you have a study where you exclude all patients with comorbidities, you very well may increase the power. But in a typical outpatient or inpatient setting, many of the patients will have comorbidities. So your research is not as relevant for the real world then. So there is a trade-off involved. For regression type designs, it's important to have enough variation of the predictor variable. So here you don't want homogeneity. If all participants of your study have more or less the same value for the predictor, it's nearly impossible to find significant effects. So it's important that for the predictor variable or the predictor variables, you have variation. For an experiment, one important point is the manipulation of the independent variable. Here it makes sense to research different possibilities to manipulate the independent variable, because a stronger manipulation can give you a stronger effect and thereby a higher power, because for a larger effect you need a smaller sample size to get to the same power. Let's say you want to look at the results of some disgust manipulation. There are of course different ways to manipulate disgust. And a manipulation that elicits a stronger disgust reaction probably will have a larger effect size and thereby a larger statistical power. You could include covariates, because covariates can reduce the error variance. For a group comparison, it can be helpful to employ a balanced design, that is, equal or almost equal group sizes. Again, an example from G-Power, 2-sample t-test. And here the allocation ratio, that is the ratio between both groups, is 1. So both groups are equal. In this case, I need a sample size of 128 to get to a power of 0.8. With an allocation ratio of 2, that is, one group is twice as large as the other, for the same effect size, now I need a sample size of 144. So equal group sizes increase your power. If you have continuous variables, in most cases you shouldn't dichotomize them. So things like median split are problematic because they reduce power because you throw out information. If you have a continuous variable, you have a whole range of values, and after dichotomizing it, you only have 2 values. So you're throwing out information, and throwing out information in most cases reduces the power. Another important topic is missing values, because there are different ways to handle missing values. In most programs, the default option is case-wise deletion, so throwing out all the information of participants who have missing values on at least one variable. But there are more sophisticated mechanisms for dealing with missing values, for instance in regression type designs, multiple imputation, and for structural equation modeling, CFA and path modeling, full information maximum likelihood. Those techniques don't throw out incomplete cases, but they take the information of incomplete cases and use those partial information for your analysis. So you have more information to use, which leads to a larger statistical power. A theoretical point, you could increase alpha from 0.05 to 0.1, for instance, but in most cases that's not an option. But for completeness sake, I wanted to add it here. You could employ a repeated measurement design, because repeated measurement designs tend to have a larger statistical power than between-person designs. So the same effect size for a t-test for repeated measures will tend to have a higher power than the same effect size for a 2 independent samples t-test. If some key assumptions of your analysis techniques are violated, you will need to use other techniques. For instance, if the normality assumption is not met for a correlation or for a t-test, you will have to choose another technique. But there are different options available, and some options that have been around for many decades that seem to be the default option for those situations aren't necessarily the options with the highest statistical power. For instance, if the normality assumption for a t-test is violated, in many cases you would choose the Mann-Whitney U-test instead. But there are other tests available with a higher statistical power. For instance, a bootstrapped t-test. The same goes for correlations. If the normality assumption is violated there, you may choose classically a Spearman correlation. But here again, there are options available with a higher statistical power, for instance Pearson correlation with bootstrapped confidence intervals. And the last strategy, in certain repeated measure designs, it can make sense to use linear mixed effects modeling instead of the traditionally used repeated measures ANOVA. So that's it. I hope that some of those strategies will be helpful for you. Thanks for watching, and see you in the next video.